Good day, everyone, and welcome to the U.S. Department of Energy's Fuel Cell Technologies Office webinar for January 2019. We've got a great presentation this month from Sandia National Laboratories and the National Renewable Energy Laboratory on HyMARC, or addressing key challenges to hydrogen storage and advanced materials through a multi-lab collaboration. My name is Eric Parker. I provide program support within the Fuel Cell Technologies Office, and I'm the organizer for today's meeting. We'll begin in just a second, but first I have a few housekeeping items to tell you about. As you may have heard, today's webinar is being recorded, and the recording, along with the full slide deck you'll see today, will be posted online, so stay tuned. Also, if you have any questions throughout the webinar that you think of, please be sure to type in your question in the chat box you should see in WebEx and send it to host, and we'll be sure to address those during the Q&A portion at the end of the presentation today. And with that, I would like to introduce today's DOE webinar host, Ned Stetson, who is joining us at DOE HQ. Hi, Ned.
Thank you, Eric. Good afternoon and good morning, everyone, and Happy New Year to you all. I hope everyone's 2019 has gotten off to a good start. I'm the program manager for the hydrogen storage activities here at the DOE Hydrogen Fuel Cell Technologies Office, and I want to welcome you to our second webinar describing some of the hydrogen storage activities we're supporting here in the DOE's Fuel Cell Technologies Office. On December 6th, we held a webinar to discuss the new activities on hydrogen carrier materials for improved hydrogen storage and transport. That presentation, slides and recording of the presentation can be accessed through the DOE Fuel Cell Technologies Office website. Today, this webinar will describe the Hydrogen Materials Advanced Research Consortium, or HyMARC for short, which we established several years ago. Today's webinar will be presented by the HyMARC co-directors, Dr. Tom Jedet of the Renewable Energy Lab and Mark Allendorf of Sandia National Lab. For a little background, in 2015, the Hydrogen Storage Program established two national lab teams, the HyMARC core team and a second team, which was dubbed HyScore. The work of the two teams was formally launched at the beginning of fiscal year 2016. So while the two teams have collaborated and worked closely together from the very start, we initially kept a firewall between them since the HyScore team was also charged with carrying out performance validation activities for our program. However, over the past 3 years, it's become obvious that there could be many more benefits if we fully integrated two teams and had them work together seamlessly rather than maintaining any firewall. And therefore, as we developed the Phase 2 program, which you'll be hearing about today, we fully merged two teams under the HyMARC umbrella. So what is HyMARC? Well, Tom and Mark will give you the details of the consortium and the work activities they have planned. I want to provide you some background and the purpose and objective of this effort. HyMARC is a consortium member of the DOE's Energy Materials Network. The Energy Materials Network is a set of national lab consortia established to facilitate access to the DOE's National Laboratories' world-class capabilities and resources to help accelerate development materials to solve challenges in various energy applications. More information about the Energy Materials Network and the current consortium members can be found at the DOE's Office of Energy Efficiency and Renewable Energy website. So as hydrogen fuel cell vehicles and other hydrogen-related applications become commercialized, the storage of hydrogen has clearly been identified as one of the leading challenges. This is driven in part by the reactivity and combustion properties of hydrogen, but is especially being driven by the low energy density of hydrogen. By mass, hydrogen has the highest specific energy, but by volume has the lowest energy density. Therefore, to store sufficient quantities of hydrogen to meet driving needs for a car, for instance, the hydrogen has to be stored at either very high pressures, current fuel cell vehicles use 7 of our 10,000 psi pressure vessels, or at very low temperatures. The normal boiling point of hydrogen is 20 Kelvin, which is minus 253 degrees Celsius or minus 423 degrees Fahrenheit, depending on your unit of preference. But even at these high pressures and low temperatures, the energy density of hydrogen is significantly less than conventional liquid fuels such as gasoline or diesel. What this means is that the storage containers are therefore very large and tend to be heavy and expensive to be able to contain either the high pressure or the low temperatures, which prevents boil-off losses. So an improved storage technology is highly desirable. Another option for storing hydrogen is using materials. Atomic hydrogen can be bound in materials through chemical bonds such as metal hydrides, or molecular hydrogen can be physisorb along the surface of porous materials such as activated carbons or metal organic frameworks. The actual density of hydrogen in many of these materials can be significantly higher than either compressed or liquefied hydrogen. For instance, aluminum hydride, also known as alane or magnesium ion hydride, these two materials, based on their crystal structure, has a hydrogen density at ambient temperature and pressure that is more than twice that of liquid hydrogen. So for years, the Holy Grail has been for hydrogen storage has been to develop materials that have this right set of kinetic and thermodynamic properties, along with other physical properties such as the hydrogen by mass, hydrogen by volume, cyclability, etc., to allow for low pressure, high density hydrogen storage near ambient conditions. However, after years of research, materials have been identified with many of the appropriate properties, but not a single material has been identified that has all the appropriate properties to be viably used in many of these applications, such as on-board fuel cell vehicles. We therefore established HyMARC to address this challenge. The National Lab Core Team is charged with carrying out foundational research to help further understand the interaction of hydrogen and materials and to develop computational, synthetic, and characterization tools to accelerate hydrogen storage material development. The National Lab Core Team is also charged with working with individual projects that are selected through either funding opportunity announcements, lab calls, or other mechanisms such as cooperative research and development agreements or CRADAs to accelerate the research progress. For HyMARC, we've had 2 rounds of 4 topics, to which we've selected 9 seedling projects to work with HyMARC on the proposed high-risk, high-reward materials concepts. Projects selected through floors, collaborate with the lab team, having access to the expertise of the researchers, as well as the computation, synthetic, and characterization resources within the consortium. Of the 9 selected so far, 8 have gone through their phase 1 go, no-go decision points. 4 have met that criteria and moved to phase 2 of their proposed programs, while 4 have not met their criteria and those projects have been ended. I want to emphasize we're looking for very challenging materials development goals, and through the 4 topics are looking for highly innovative, although scientifically feasible, high-risk, high-reward research proposals. We therefore expect a high percentage will not progress past the first phase of the program. So that's just a little bit of background on HyMARC. I'll now turn it over to the HyMARC co-directors to tell you more about the consortium itself and the research plans. Dr. Mark Allendorf is a senior scientist at Sandia National Laboratories. He is a chemist with degrees from Washington University at St. Louis and Stanford University. He's a president emeritus and fellow at the Electrochemical Society and has received a 2014 R&D 100 Award for a novel approach to radiation detection. Dr. Tom Jeanette holds joint appointments as a principal scientist at Renewable Energy Lab, as well as being a professor and department head of chemistry at the Chemistry Department, School of Mines in Colorado. He is also a chemist with degrees from State University of New York in Potsdam, and also from my alma mater, the University of Vermont. Prior to joining NREL, he was professor for 18 years at the Rochester Institute of Technology, and he currently holds the title of emeritus there. So with that, I'll turn it over to, I believe, you, Mark, right?
Hello, everyone. This is Mark Allendorf. It's my pleasure to give this overview of HyMARC. Before I do that, I want to thank Ned first for that introduction, but also with his colleagues Jesse Adams and Derek Colby for their very strong support of this effort, and of course for the funding from EERE's Fuel Cell Technologies Office. Next slide, please. This is a brief outline of the material I intend to cover. Ned's already given the fuel cell technology intro and covered some of the overview of HyMARC, but I'll reiterate a little bit of that in terms of the goals and tell you a little bit about the phase 1 accomplishments. We're referring to phase 1 as the previous 3 years, so that's fiscal year 16 through 18. We're now in phase 2, which is projected to last for another 4 years, starting this fiscal year. So I'll tell you a little bit about our research tasks and some of the projects that are involved, and then I'll get into HyMARC capabilities, which is an important deliverable of the HyMARC effort. And finally, I'll give you a few brief examples of some ongoing research and try to wrap that up with 15 minutes or so left for question and answers. Next slide, please. So as shown here in this hexagon at the top, HyMARC is comprised of 6 national laboratories. As Ned said, the core team originally in the first phase was Sandia, Lawrence Livermore, and Lawrence Berkeley, but that has now been merged with 3 other, with Pacific Northwest Lab, NREL, and a second effort at Lawrence Berkeley. We are also closely aligned with the neutron facilities at NIST. There are 2 HyMARC-funded postdocs there, and also with user capabilities at SLAC. So this is the research team that comprises HyMARC. You see below there the icons from various seedling projects, and the arrow going both ways is intended to indicate that HyMARC and these projects collaborate very closely with each other. I'll tell you a little bit more about the roles of HyMARC in assisting these projects and trying to help them meet their go, no-go milestones. But in general, the objectives of HyMARC are to first develop and enhance what we call core capabilities for hydrogen storage research. This is in particular computational models and databases, new characterization tools and methods that can probe basically all relevant length scales of hydrogen storage materials, and then tailorable synthetic platforms that are designed to be reproducible and also allow us to probe specific aspects of phenomena such as nanoscale confinement and processes on surfaces. But a second important aspect of HyMARC is to validate results that are produced either by the seedling projects or other work throughout the world on hydrogen storage, and also to validate our own theories and models for hydrogen storage. This is quite crucial to a strategic plan of FCTO, which wants to invest its funding as effectively as possible. We, of course, also want to accelerate the path forward to developing hydrogen storage materials, and the rest of the presentation hopefully give you a sense of how we go about doing that. Next slide, please. So this is just a little introduction to some of the individuals that are involved. The pictures and names here are of the PIs at the different laboratories and their primary investigative assistants. You can see some of these names may not be familiar to you, but all have long track records in the hydrogen storage field or in specific areas of characterization, such as the neutron work at NIST and X-ray work that's being done at SLAC. Next slide, please. So as Ned mentioned, just a little bit of history. About 4 years or so ago, FCTO convened a workshop of major players in the hydrogen storage research field and asked the question, why is it that we don't have any materials at that time that can meet all of the DOE technical targets? And there are a variety of reasons, but one of the main ones is that we still lacked a great deal of fundamental understanding of the processes that control the properties of these materials. And by properties, we principally mean the ability to release and uptake hydrogen and do that in a way that meets these targets. So you can see on the right there, the spider chart shows these various targets, and the ones that are underlined in red are ones that HyMARC has particularly been focusing on. It's important to remember that HyMARC is not specifically driven by targets, but we are trying to solve problems that are preventing people doing materials discovery from reaching those targets, and that's why we've taken a little bit of a step back to do more foundational research, as we call it. So the ways that we can accelerate materials discovery include strategic assessments, which means that we look at different strategies for developing or improving materials. We try to provide thermodynamic and other data that are either missing or known to be inaccurate. And there's some specific examples I could show you relating to metal hydrides, for example. Modeling tools are essential and have primarily been focused over the past years prior to HyMARC to thermodynamic calculations involving primarily density functional theory. we've gone many generations beyond that to be able to look at, as I said, all relevant length scales. And then finally, we assist these seedling projects, and we do that in several ways. One, we provide access to experimental resources that are unique to HyMARC, but vital to their success. We do provide computational modeling assistance in support of some of these projects, and in some cases with data interpretation, in particular cases where spectroscopic tools that we have can help identify species more definitively. Next slide. So the two primary categories of hydrogen storage materials that concern HyMARC are metal hydrides and sorbent materials. And this little cartoon here gives you some sense of the complexity of the phenomena that are involved. And in fact, when HyMARC was first launched, we were tasked with looking at all relevant phenomena, which covers everything from the interaction of hydrogen with the surface to its transport into the bulk, which could be by diffusion through solid or through pores in something like a metal organic framework, to chemical reactions that lead to the nucleation and growth of new phases. You can break this down into essentially two pieces. One is the thermodynamics, and the other are the kinetics. And the EA activation energy there, within that are subsumed all these different processes that could contribute to what is the real energy required to desorb hydrogen or reabsorb it to regenerate the material. So hopefully this gives you a little bit of a sense of not only how comprehensive HyMARC's effort is in this area, but also how complex the problem is. And it really explains why, until now, it's been so difficult to meet all of these technical targets. It's a very challenging problem. Next slide. Nevertheless, and can you hit that twice, please? There we go. Nevertheless, we have really had some successes, some significant successes in what we say is moving the bar for specific materials and strategies. And it's important, I think, to understand what the bar is now. There are, of course, the DOE targets, but as many of you are probably aware, there are now commercially available hydrogen-powered fuel cell vehicles, and these store hydrogen by using high-pressure carbon fiber reinforced tanks. The pressures involved are as high as 700 bar, and this, of course, is expensive from both the point of view of the fueling station, but also the manufacturer of the tank, and it places a lot of constraints on the design of the vehicle. So really, one of the bars is to develop materials that can beat compressed gas, not only to meet the DOE targets. And so we've tackled a number of different strategies, and I'll show you just a few of them are listed here. You know, metal hydrides in particular, their complexity has been a steep hill to climb, but we've been looking at various strategies that can help us improve the thermodynamics and kinetics. An example of that is our efforts to probe the interfaces between hydrogenated and dehydrogenated materials. And this has resulted in some cases where we've had really remarkable reductions in the heats of desorption that are required. Lithium nitride is an example where our understanding of the nanoscale effects of these interfaces allowed us to reduce the cycling temperature by over 180 degrees C. In the area of sorbents, HyMARC can actually claim the development of the sorbent with the highest volumetric and gravimetric capacity at room temperature. And this is really the holy grail, is to be able to store hydrogen at ambient temperature so we can eliminate the use of cryogenics, and of course to do it at lower pressures. So you'll be able to look at these slides offline and see some of these. If you have questions about the specifics, we have published a number of articles, but Tom and I would be more than happy to answer questions about those. So let's go to the next slide. As I mentioned, publications are a very important product of HyMARC, and to date, we've had over 50 publications. I'm highlighting a couple here that I think might be particularly useful to you. One of them is a perspective article that we published in the Energy Environmental Science Journal just last year, and this is our assessment of various strategies for developing adsorbent materials for vehicular storage. This is a topic that has encompassed a very large range of strategies over the years, some of which have we've concluded are not going to be effective, but others, the jury is still out. And so we attempted in this article to give our perspective on that, to cite some relevant literature, and give a little bit of a prognosis. And this is intended to provide information to DOE to guide future FOAs that would be designed to develop new materials. On the right-hand side there is a sort of counterpart dealing with nanostructured metal hydrides. Nanostructuring is actually in our research has been shown to be one of the most effective ways of improving the kinetics or shifting the thermodynamics of metal hydrides. And we conceived a review article that we actually thought would be relatively short, but we're astounded to realize that there were hundreds of papers out there just within the last 5 years. This review, I think, has something like 550 references, so it's very comprehensive. We're optimistic, actually, about this strategy, and I think if you take a look at this, you'll get a sense of just how promising it can be and how exciting some of the developments are. Next slide, please. So Ned mentioned the seedling projects. The seedlings are small efforts, relatively small, that have an initial phase of 18 months to evaluate a particular strategy, a well-defined strategy, answer a specific question with a go, no go at the end of that 18 months. And if that go, no go is reached, then an additional 18 months of funding can be provided to pursue it further. So what HyMARC has done and it continues to do is to assist these by, first of all, giving a designated HyMARC point of contact. And this is important because the whole team of HyMARC, I think, is over 40 people now. So it would be difficult to figure out just where to start if you had a specific question or need. We, of course, provide technical expertise concerning specific scientific issues and access to HyMARC capabilities. But I should say that this access is something that we agree on in concert with DOE, NED in particular, and we want everyone to know that HyMARC is a standalone research organization. It's not an analytical service. So we encourage these seedling teams to dialogue with us carefully and plan experiments, which it can in fact involve visitors, students, whatever, actually to HyMARC laboratories. But we want to plan these very carefully so that the best use of these, in many cases, scarce resources can be made. The 4 seedling projects listed below are the ones that Ned mentioned are now in their phase 2 effort. And an example of what we've done for some of these, the one with the University of Hawaii, we took samples that they sent us and exposed them to ultra-high pressure hydrogen using a facility that we have here, and then assisted them with some characterization of that. In other projects, we've done modeling, for example, that has assisted in the interpretation of data by the project. we also have taken prepared samples, for example, from NWEL, where they've used ALD and infiltrated them with a metal hydride to create this composite material. And with all of the projects, the ones that started and are ongoing, we maintain a fairly continuous conversation with them about their progress. So this is really intended to be a collaborative effort, and we publish joint publications and have visitors to the various labs, as I mentioned. Next slide, please. So HyMARC has a task structure in phase 2, and it's broken down as shown here, first by material categories, sorbents, which is led by Tom Jeanette, and metal hydrides by myself. Hydrogen carriers is also a key element. That was covered in an earlier webinar, which there's a link there if you're interested. We have another task that's focused on the development of advanced characterization capabilities led by Phil Puria at NREL. We have an effort to specifically support the seedlings. And then finally, we are bringing online a data hub, which is not open to the public at this stage, but I believe it eventually will. And the intention here is to collect data that can be valuable to the research community at large. Next slide, please. So within this phase 2 research effort that we just launched, we have a number of what we call focus areas. And these are intended to be things with, or topics with a starting point and an ending point. Some are larger efforts than others. Some are effectively exploratory kinds of efforts where we're trying to decide whether a particular strategy is going to pay off or not. You can see a list of the overall topics here. In the area of sorbents, much of the effort is focused on either improving the binding energy of hydrogen or the free energy, not just the enthalpy, to a sorbent, but also trying to develop strategies for packing these in an efficient way so that there's no loss of capacity due to macroscale pores between particles. We're, of course, also looking at trying to increase the capacity, and one of the principal strategies is to develop materials that can bind more than one hydrogen to an active site, such as an open metal site on a MOF. In the area of metal hydrides, it's broken down a little bit more along the lines of specific phenomena, thermodynamics, of course, but also interfaces that can be either on the surface or in the bulk, strategies for activating bonds such as boron-boron or boron-hydrogen bonds that are quite possibly rate limiting in the ability to desorb or reabsorb hydrogen. And things like nanoscaling and microstructural effects that are both chemical and physical in nature. The advanced characterization efforts include some very specialized facilities at NREL for doing calorimetry, NMR spectroscopy at Pacific Northwest Laboratory, which has capabilities for looking at isotopes like boron and also solid state NMR. And also we have access to various DOE user facilities and some other specialized methods that we've developed ourselves that I'll tell you a little bit more about. So next slide. So I want to just give you a quick overview, a sense of the capabilities that HyMARC now has available. Modeling has been a very crucial tool. As we show here, we now have models that can address length scales that range from sub-nanometer, which is, of course, chemical bond lengths, but also things that affect spectroscopy, like X-ray techniques, up through the molecular micro scale, mesoscale, and even up to grains where we're now talking about micron scale materials. And then finally, bulk properties, which are essential to understanding, at least in a first order sense, the behavior materials, and I show a thermodynamic phase diagram there for magnesium borohydride, where we were able to combine a model with experimental data that we obtained to really upgrade and revise that understanding of the thermochemistry of that material. Next slide. So characterization tools are also critical, and again, these match the length scales of the models, but we're using cutting-edge tools that were either not widely available when HyMARC started 3 years ago, or not available at all. And some of the ones that are illustrated here are soft X-ray tools at the advanced light source, for example, which allow us to probe coordination environments among light elements, but also very sophisticated electron microscope tools, X-ray microscopy tools shown there under the mesoscale column that allow us to look at phase evolution, and then these more macroscale tools such as a high-pressure reactor that provides both a way of characterizing behavior under these ultra-high pressures, and in this case it's up to 1,000 bar. We can also look at the exchange of hydrogen, isotope effects, which help us look at the kinetics of the reaction of hydrogen with these materials. Next slide. An example of where we have particularly deep capabilities is in the area of surface chemistry. Of course, hydrogen has to interact with the surface of any storage material. That's the first thing it does. But there's sort of a misconception that some analytical tools that are widely used, like X-ray photoelectron spectroscopy, are able to actually detect hydrogen at the surface on the monolayer surface. That is actually not correct. X-ray XPS is actually probing several nanometers into the bulk. So HyMARC actually has access to an instrument at Sandia called low energy ion scattering, and this tool can actually look at the atomic monolayer and it can detect hydrogen specifically. It's the only diagnostic tool that is capable of doing that. So we can see hydrogen as it absorbs and dissociates on a surface and interacts with various elements that are present there. What can we learn from this? Well, of course, we can look at the exact surface composition, but we want to know how these surfaces respond to changes in temperature in the hydrogen environments. We'd like to look at the spatial distribution of different species and ultimately answer the question, can we modify or tailor these surfaces to improve hydrogen storage properties? As you can imagine, these are pretty foundational questions, but they are really essential to getting a handle on how these materials behave. Next slide, please. So we have some, again, unique capabilities within HyMARC that are experimental in nature. One of these is the DRIFT capability, diffuse reflectance infrared Fourier transform spectroscopy. This is a tool that allows us to look at the binding of hydrogen to a material such as a sorbent and correlate that binding with different binding sites. We can also do very detailed thermal conductivity measurements. This is crucial for aspects of the heat balance when we are loading hydrogen or desorbing it from the material. And then finally, variable temperature, or PCT, which is a method for getting thermodynamic data for the uptake and release of hydrogen from various materials. The instrument that's shown here can access hydrogen pressures up to 200 bar and temperatures up to 350 Kelvin. I want to also emphasize, though, that we're not limited to looking at hydrogen. We can also look at other gases using these instruments, such as methane and CO2, and we have a suite of other characterization techniques, the sort of usual suspects, such as BET and various synchrotron-based techniques that can also probe these. So we have a quite versatile toolkit here to provide insights into these materials. Next slide, please. so this is also one unique both characterization and synthetic instrument that we have. This is the high-pressure hydrogen reaction station that is in Sandia, California. This instrument, actually I was informed yesterday, can actually go up to 2,000 bar and hold up to 4 samples and heat them up to 400 degrees C. What's interesting about this is that it now provides us a way of looking at the behavior of materials at pressures that are now accessible in commercial fueling stations. Not that we think that necessarily that 700 bar is the optimum, but it is interesting to us to be able to push these materials as far as we could conceivably go with available commercial equipment. And in some cases, this may allow materials, certain metal hydrides, to become able to meet DOE targets that could not make those targets back when the limit was something like 100 bar. Next slide. So this slide gives you a little overview, again, matching the length scales, where now these are synthetic capabilities that are designed to probe specific aspects of storage materials. And they've allowed us to discover some interesting, unexpected phenomena. For example, using the high-pressure reactor, we were able to show that there's actually a liquid phase of magnesium borohydride. There's some little pictures there you can see of it. And this provided thermodynamic data that filled in some important gaps in the phase diagram. On the other end of the spectrum, though, we've developed very well-controlled carbon materials, such as these graphene nanoribbons that are shown here. And these allow us to probe both the interaction of hydrogen with the surface in a way that is far more controlled than would be in a porous carbon, but also we can functionalize the edges of these with catalytic elements and look at the reaction of hydrogen in this very controlled environment, free of a lot of complicating issues that are endemic to disordered materials, what various kinds of absorbents, not just carbon. Let's see. Next slide. I want to speed up just a little bit so I make sure we have time for some questions. I did mention that HyMARC has access to several user facilities. The emblems of these are shown here. In some cases, we have essentially dedicated access. NIST and its neutron facilities are an example of that. In others, HyMARC is essentially no different than any other user. We've had to write proposals to obtain access to these tools. And an example is the Advanced Light Source. We were very fortunate in the first phase of HyMARC to have what's called an approved program at the ALS, which gives us some dedicated time over a period of 3 years, and we're hoping to get that renewed for another 3 years. It may be possible in some limited circumstances for example, FOA projects, new seedlings, to interact with us and obtain some data from there. But by and large, these are tools that are limited access that are mostly focused on these very fundamental questions that the HyMARC team is working on. The next slide, please. So let me just give you 3 short examples of experimental activities that we've been engaged in. Next slide. So sodium aluminum hydride is a sort of canonical metal hydride. It's been studied extremely extensively, and particular its interaction of certain catalytic elements or additives such as titanium. You would think that everything is known about this material that could be known. Taking the example of the titanium additive, there's something like 2,000 papers out there that have addressed various aspects of this. Well, we were able to apply this suite of surface and bulk characterization tools coupled very closely with computational spectroscopy, and we figured out a couple of things about this that were really not suspected. One is that titanium, whatever its role is in the desorption, it's not occurring on the surface. We don't see any titanium species on the surface of this material and during the process of desorption. And we were able to probe that several ways, the low energy ion scattering, but also ambient pressure XPS experiments at the ALS. But the other thing that we learned, which really came as a surprise to us, is that there are oxygenated species on the surface of this material that appear to accelerate the desorption of hydrogen. They are, in fact, essential to the behavior of the material. And the prejudice, I think, or preconceived notion up till now has been that oxides are bad. They contaminate the surface. They can, if they're too thick, of course, they can block the access of hydrogen to the rest of the material. These experiments and calculations suggest that under controlled conditions, one may actually want an oxide layer, a very thin oxide layer, and we're looking at that now in other hydrogen or other metal hydride materials to see just how general that phenomena is. Next slide. I mentioned borohydrides. Borohydrides are attractive because they're light and their gravimetric and volumetric capacities can be very competitive, but they are also incredibly complex materials. Taking magnesium borohydride as our starting point, these materials have complex decompositions that produce molecular species, closoboranes, that these are kinetic intermediates, and it was baffling for years trying to figure out how to stop this from happening, what was controlling this formation. So what you see here is some modeling that we did, and this again was correlated with experiments that allowed us to look at the very early stages of the rehydrogenation of magnesium diboride. And what we learned, in short, is that there are different, essentially defect sites in this material, basal planes where there may be magnesium or boron exposed, and the reaction of hydrogen with those sites has different activation energies. That's what's shown kind of exhibited down here in this lower left-hand corner. And essentially what we see is that the activation energy evolves with the extent of decomposition of the material. So again, this fundamental insight allows us to now conceive of strategies where we can try to force the material to go one direction rather than another. And in particular, the hydrogen interaction with these sites, these boron-rich edges, seem to be the ones that lead to these kinetic intermediates. So finding a way to cap those off is one strategy. Next slide, please. Finally, something about sorbents that makes use of this really powerful drift capability that we have. Probing the adsorption sites of hydrogen within a porous material is extremely difficult. It can be done to some extent with NMR. Neutron tools are very effective, but what we can do now with this drift is get simultaneous chemical and spatial information that can be straightforwardly compared with modeling. So what's shown here are some vibrational spectra taken with this drift instrument for a high capacity MOF called cobalt DOBDC, and this material has two different adsorption sites, and we can pinpoint those by using the vibrational spectrum. So you see that in the right-hand plot there. The more strongly binding material or site is the one on the right, I believe, and then the more weakly binding one, which fills second, is the one on the left. And so you can see in the essentially the isotherm plot that's shown there on the left how the material fills up one site and then proceeds to the next one. So we are getting data here that we couldn't really get any other way, and is now helping us design these sorbents in a very rational way with effectively design rules for the material. Okay, so let me just summarize very quickly. HyMARC is a national laboratory consortium with a big team of people with various interdisciplinary expertise. Characterization tools, modeling, synthesis are all important elements. But we also collaborate extensively both with these seedling projects and externally, both nationally and internationally. to offer scientific expertise, joint experiments, and access to these cutting-edge capabilities. So I hope this has been informative to you, but there's some opportunity here now to ask questions. Please feel free to do that, and thank you very much for this opportunity to tell you about our exciting work.
Thanks, Mark. We're going to open up the Q&A portion of the webinar now. Please, as a reminder, if you thought of any questions during the presentation, please submit them now, and we'll get to as many as we can. Ned, do you want to take it from here?
Thank you, Eric. So we do have a question here concerning interactions between the Seedling projects and the core team. From your experiences, how have the interactions gone, and what has been the most productive interactions between the Seedling projects and the laboratory teams?
Well, I think Tom and I can both answer that. I'll give an answer first. Really, the most, I think, productive and effective interactions have been ones where we, through careful planning, defined a very high leverage set of experiments where samples are sent to us, for example, and optimally where an investigator from the Seedling project actually comes to the HyMARC laboratory to interact face-to-face with the research staff. Really, that's the best way to do it. Now, that isn't always feasible. I think the key element is extensive communication, number one, and two, careful planning so that the best use of the time and the resources are made. Tom, you have anything you want to add to that?
Mark said it very well. Thank you.
Okay, next
Thank
question.
You. So we have another one here. There's a question about the purity requirements for hydrogen gas. The questioner is trying to initiate a new project to develop flexible high-temperature fuel cells that can be switched between power generations and hydrogen generation. There are many challenges. One of them is to efficiently separate hydrogen gas from CO2. So have you looked at or considered hydrogen selectivities?
Hydrogen selectivities?
So I'm assuming it's to be able to selectively separate hydrogen from other gases, in this case CO2.
No, we have not actually looked at that. I think the closest we've come to addressing the questioner's issue is the work where we've looked at the oxygen on the surface. Tom, can you comment on maybe some competitive binding or other efforts that have gone on at NREL?
Not in the HyMARC program. We don't typically work on competitive binding with the different materials at this point in time. It is something that we would look at in the future as you're starting to deal with some of the high-end sorbent materials to see what you could tolerate in your hydrogen stream for some of the other gases that might be present.
Okay, thank you. So I'm looking at the various questions. So one question, I guess, is for you, Tom, about the validation measurements. If a project had a material that needs to be sent to NREL, how could one be sent to them? Can you give any details on how a project could have a material performance validated? And I guess there's two types. There's the Seedling projects or projects associated with the HyMARC and the DOE program, and then there's projects or entities that are not associated with HyMARC and the DOE program.
So with the DOE-funded projects, it is usually for a go, no-go decision, and those materials would be the best materials that whatever project had. They would be coordinated through the DOE program manager, and then we all work together to make sure we have all the criteria. Typically, whoever the scientists are come out to make sure that all the sample preps and everything are being done correctly, and then we go forward with the test that way. It typically takes about 3 weeks to get a complete validation done at the various, whether it's at 77K or any of the other temperatures that would want to be done. When it comes to having non-DOE samples, we are contacted. We always request initial data before we would start, and then depending upon what the individual would want tested, there is a certain cost structure that we have set up that we would be happy to share with them at that time.
Okay, thank you. So another question, can the HyMARC people, capabilities, and resources described here be applied towards electrolysis process materials in terms of cathode and anodes? So you think expanding beyond hydrogen storage materials into hydrogen generation materials, I guess.
Well, I guess in principle, but that isn't really in our mission space. There is an EMN electrocat that I think would be more suitable for that.
Actually, there's another EMN hydrogen, which is led by NREL, which actually may also be more suitable.
Both, yeah.
Okay, there's been a number of questions submitted concerning working with HyMARC or future funding solicitations. So I'll actually respond to those, take those myself, and kind of group them all together. So far we've had 2 rounds of seedling projects selected through funding opportunity announcements. We anticipate that there will be additional topics in funding opportunity announcements in the future. So all I can say there is just watch. I recommend everybody that's interested to go to the Fuel Cell Technologies Office website and sign up for our email blast, our newsletter, because we will be announcing any funding opportunity announcements coming from the office through those, so that'll give you a heads up. So I recommend that everybody sign up for that to get the heads up for any opportunities coming out of the office. The other way to work with HyMARC is through cooperative research development and development agreements, CRADAs. Those are actually negotiated between the HyMARC team and usually a company, and there's these specific requirements within the CRADA itself. For all the EMNs, we've been establishing standard CRADAs, so it's a streamlined process, so it removes a lot of the burden and difficulty of trying to negotiate CRADAs that we've had in the past, because we've actually tried to standardize it so there's minimal negotiation. Just like our non-disclosure agreement that we have for the EMNs, it's basically a take it or leave it. We try to streamline it so there's very little negotiation or changes mediated between one seedling project and another project with the HyMARC labs. So if you're interested in working with HyMARC,
sorry, this is Eric. If everyone's viewing the slides, the link at the bottom of the current slide, if you sign up for that, you'll be updated on the topics Ned just discussed.
And then the other way to work with HyMARC is if you have, for instance, a specific characterization need, such as a material absorption validation, then NREL in particular has a mechanism set up so that individual companies or researchers could go in and actually have samples measured. However, there is a cost associated with that. Let's go. Okay, so has HyMARC been involved in researching aluminum hydride aniline? And if so, what were the results?
Well, we're not working on aniline specifically right now. There was a seedling project that had a strategy for looking at that unfortunately didn't make it past its first go no go. There was some published work out there on this. It is a promising material, but right now we're not directly working on that.
All right, thank you. I just had another one which I just lost. Well, there's one here, I guess this is for you, Mark. I'm assuming this is related to the high pressure system. And the question is, how do you get to 2,000 bar and how do you measure the pressure? I think there's a 1,000 bar is the actual limit of the system, not 2,000, but.
Well, you get to that pressure with some specialized compressors that we have, and then the pressure is measured, I believe, with mechanical gauges. But I have to tell you, I have never done it, so I'm only telling you from the bits that I know. If the questioner has some specific questions about it, I'm more than happy to put you in touch with the person who really knows all the answers.
All right, and we actually only have one more question here at the moment, so if you have any more questions, please send them in. We have time for a couple more, but right now we have one more, and it kind of relates to an earlier question: is how do small businesses get involved or benefit from HyMARC, and is it possible? And again, I think that is primarily the two ways a small business get involved is either through a funding opportunity announcement, applying to a topic and being selected for funding and support from the DOE office and working with HyMARC, and the other is to set up a CRADA with HyMARC to work directly with them through a CRADA. So with that, that's all the questions that we've received so far. So if there's no more questions, then I think I'll turn it back over to Eric and for her wrap-up.
Yeah, thanks, Ned, and thank you to everyone who asked a question. We did just get one last one. We have time for one more. Ned, or Mark, have neutron techniques been applied to monolayer sensitivity?
Neutron techniques. Not that I'm aware of.
Okay, thank you. And if anyone thinks of any more questions, go ahead.
I just was, in my little question box here, I see one other question that appeared concerning power to gas projects. Do you see that one?
No, but go ahead and address it if you can do it in a couple minutes.
Well, let's see. In various power to gas projects, there is interest in storage of methane hydrogen mixtures. Example, 80% methane and 20% hydrogen. Does the DOE or HyMARC have any interest in this? I would say, in principle, yes. And one of the things that we're starting to work on are hydrogen carriers. We're not specifically considering mixtures right now, but it could evolve to that. The issue being that hydrogen is such a low volumetric density that even a high pressure tanker truck can't move very much of it. So we're looking for ways to chemically and reversibly bond hydrogen in a bulk material that's cheap enough to use as a transport medium.
Ned, I think we had one more come in. Our last question for the day.
All right, you've sent it to me?
Yep.
All right, it's looking at materials for large-scale storage. And actually, that was the subject of the prior webinar we had on December 6th. As Mark and Tom mentioned, we are working on hydrogen carriers now. So hydrogen carriers are not being looked at for onboard a vehicle. It's actually being looked at for the bulk storage and transport of hydrogen. So if you're interested in large-scale storage, I recommend that you go to the DOE website and look up the webinar from December 6th, which is specifically on hydrogen carriers. And as you saw early in the presentation, the hydrogen carrier work is a task within HyMARC. However, it's one of the newer tasks and one of the new areas the program is getting actively involved with, and therefore we actually had a separate webinar on it. But that is specifically looking at materials for bulk storage and transport, and it will be a similar program as the projects that Mark was describing earlier, where we will run a forward topic and select projects through as seedlings to come in with a high risk, high reward, innovative concept to work with the laboratory team. We'll take it through the first phase to see if the project seems feasible or not. If the concept is feasible, then we'll support it for additional research. If it's not feasible, then we'll wrap it up at that point.
Okay, I'm going to have to finish up there. Sorry if we didn't get to your question. We do have to cover a few housekeeping items in the last minute we have. First of all, please, as a reminder, the AMR this year is taking place from April 29th to May 1st in Crystal City, Virginia. Please visit the website there and get information. And then, again, please sign up for our newsletter to receive updates for the fuel cell and hydrogen energy program. And with that, I'd like to thank everyone for joining. Please feel free to email us with your specific question or concern if we didn't get to it. And as a reminder, again, this was recorded and the webinar and slides will be available online. And I encourage everyone to sign up for the monthly newsletter to find out about future webinars. And with that, have a great rest of your week, everyone, and goodbye.